Okay, after a 5-minute break, let's start section 4, some simple propositions about the probability, and we are going to do some simple proof of those propositions. Now let's be clear about the mutually exclusive event first, okay? Mutually exclusive event. Then we can understand the proof. Okay, sorry, we can understand the idea of the proof in a better way. So now let's look at event E and E's complement. Both are event, right? Both are event. E's complement is also event, right? Is also event. So if we have the, let's use the Venn diagram, okay? Let's use the Venn diagram. So this rectangular box represents the sample space, and then we have the event E, okay? This circle is event E. Now, what is the E's complement? E's complement means all the events in the sample space, but not in E, right? Not all the event, all the outcomes in the sample space, but not in event E. So that will be the shaded blue part, okay? That is all the outcomes in the sample space, but not in event E. So this will be E's complement, right? E's complement. Now, can we call event E and E's complement are mutually exclusive? Can we call those? Okay, let's check. E and E complement. Any intersection, any outcomes occurs in both? Yes or no? Any outcomes occurs in event E and also in event E's complement. This E event, yes, any outcomes occurs in both. It's null event. Yes, very good. It's null event, right? Because event E represents the circle. This circle, right? That is event E. That is event E. No outcomes from the both. Yes, no outcomes from the both. So we can call it, it's null event, right? It's null event. Because the event E is the outcomes inside the circle, and then the E's complement is also an event. E's complement is also event that consists of the outcomes in the sample space, but not in E. So it's outside of the circle, but in the box, right? In the box. So those two events are the intersection of those two events, or we call the E and E's complement, are null event, right? Null event. What does this mean? What does this mean? E and E's complement, they are null event. So we can call E and E's complement are mutually exclusive. So everyone, any problem to check my note? Any problem to follow my note in the Rain classroom? Please let me know, okay? Please let me know. If there is a lot of buffering, then I can write it in a slow way, okay? I can put my pace in a slowly. So no buffering. Okay, very good. So event E and E's complement are mutually exclusive. So this is true. Actually, this is true for any event in the sample space. Okay, any event. For example, any event F, which is the subset of the sample space. How about F and F's complement? So we take any event, okay? We take any event which is a subset of the sample space. What is the relation of event F and event F's complement? Still, okay? Still mutually exclusive. So trying to understand this mutually exclusive. And by the way, the mutually exclusive show two events, okay, two events. Those are two events. The two events mutually exclusive, which is showed in the Venn diagram, is just you separate. You divided the sample space, this box, in two parts, right? Like the two colors I did here. One is the circle, that is event E, and the other is the blue part, is event complement. So you can do the same thing for event F in the sample space, right? F, you use one color, and then the other part outside of F in the sample space in the rectangular box will be F's complement. So now, is everyone clear what is mutually exclusive? And especially one event, any event in the sample space is any event in the sample space and its complement are mutually exclusive. By the way here, especially if this event, if the event E is the sample space, if the event E especially is sample space, what is E's complement? What is E's complement? Can you tell me that? So which means in the whole box you are going to draw in the purple color, right? You are going to draw in the purple color. And then what is E's complement? What is the complement of the sample space? Do we have any outcomes in the sample space complement? Null event, right? Null event. Makes sense? Yes. Null event, right? If especially my event E is the sample space, then E's complement will be the null event. Now, let's check the proposition. And in Chinese, the proposition is called 命题. We did some Chinese characters, right? Axioms is called 公理, theorem, 定理. And then proposition, 命题. 4.1. Probability of event E's complement equals 1 minus the probability of event E. Okay. Now let's analyze this one. Okay, it's a pretty easy one. We can prove it with the axiom 3. Okay, with the axiom 3. So here, especially we know that. Okay, we know that. Let me just write my proof. Okay, let me just write my proof. So the sample space, okay, the sample space will be the event E union is complement for any event, okay, for any event. I think this is true, right? From the previous Venn diagram. For any event which is the subset of the sample space, then you can write the sample space. You can write the sample space is the event E, which is the circle, union the other part in blue color, right? Inside the rectangular box using the Venn diagram in the previous slides. Make sense? This one, okay? So the sample space actually divided into two parts. The circle, which denotes the event E, inside the circle, right? Shaded circle denotes the event E, and the outside of the circle, that is event E's complement. This is also called the event, right? This is also called the event. Now, we understand that the probability of sample space is 1 according to axioms 2, right? Axioms 2. Now I can let E1 equals event E. E2 is E's complement. And we know that those are all event. Those are both event, right? E and E's complement. And what is the relation between E and E's complement? Mutually exclusive, right? Mutually exclusive. That means the intersection of those events are null event, right? Null event. So event E1 and E2, they are mutually exclusive according to axiom 3. According to axiom 3, follow axiom 3. Any problem? Any buffering problem to follow my notes in these slides? Please let me know, okay? Please let me know. You can either reply in a group, in a WeChat group, or as the comment, as your reply in the 弹幕. Follow axiom 3, we can write P E1 union E2, right? That is the union of two events. We can write in this way. Probability of E1 union E2 equals the sum of each event, right? The sum of the probability for each event, but my I from 1 to 2, which is just PE1, PE2. The reason I just write the event E1 and E2, trying to make my event notation in the same way as the axiom 3, okay, as the axiom 3. So now what is the E1 union E2? What is E1 union E2? Let me just all right, let's just continue the same color. So what is the E1 union E2? E1 union E2 is the event E union event E's complement, right? And we know this is the sample space, right? This is the sample space. What is the probability for the sample space? It's 1, right? It's 1. Sample space. The probability of sample space. And then PE1, that is the probability of E. PE2, that is the probability of E's complement. So the sum of the probability of event E plus the probability of E's complement is 1. Then how about probability of E's complement? Of course, 1 minus, right? 1 minus. That's why we explain the E and its complement, the event E and its complement. The union of those two events are sample space, but the intersection of those two are null space, okay, are null event. Sorry, it's a little noise with the airplane is flying in the sky of my local area. So let's make a note here, okay? Let's make a note here. So any event subset of the sample space E, okay? Any event E and E's complement, null event. E and E's complement is null event. E union is complement sample space, okay? Sample space. And if they are mutually exclusive, we can apply the axiom 3. This is the special case for axiom 3. We only have 2 events, and the axiom 3 is true for the case 2 we discussed. It's true for any finite sequence of the event, E1, E2, En. Or it can be more general. It can be also true for the infinite number of sequences, E1, E2 until E infinity, like that. So that is the simple proof of the proposition 4.1, and I think it makes sense, right? It makes sense. The probability of E's complement equals 1 minus the probability of event E. And from here, you can check that the probability according to axiom 1, probability for any event is between 0 and 1. Okay, according to axiom 1, probability for any event should be between 0 and 1. And I think it's easy to understand this part by chance, right? By chance. If you understand it as a chance, so of course it's between 0 and 1. And it can equal to those two numbers. Now, proposition 4.2. If event E is the subset of event F, two events, then the probability of event E is less than or equal to the probability of event F. Here, be careful about those notations, okay? Be careful of those notations. Event E and event F, those are basically just the sets, so we use those, okay? We use those symbols. E is contained in event E is contained in event F. But here, probability is the set function, is the number between 0 and 1, so we can compare in the numbers. Make sense? But those are event again, okay? And of course they are subset. They are subset of the sample space, okay? They are subset of the sample space. So let's use a Venn diagram to understand the relation of those two events, E and F. Here I have event F, which is a big circle because event E is contained in event F. This is my event F. Now let me use a different color in blue. So event E is contained, okay, is contained, which is a subset, that is E, okay, that is E. So this blue color is event E. So this is represented by Venn diagram, right? E, of course, E is a subset of event F. So the probability of event F, the probability of event E will be less than or equal to probability of event F. Now, it's easy to understand like that. E consists less number of outcomes than event F, right? Than the event F. Or it might be the special case when equal. When they are the same, it's equal, right? It's equal. Now how can we prove this one, okay? How can we exactly prove this proposition 4.2? So we are going to rewrite the event F in this way, okay? Proof E is a subset of F, okay? E is a subset. Rewrite event F in this way, okay? I'm going to rewrite event F in this way. So here you will notice that the event F will be two parts. The part is in blue. The part is in blue is in event A, and the part out of the blue circle, okay? But this circle is not E's complement, right? Be careful. This one outside of the blue circle is not E's complement because this part is still contained in event F. It's not all the part in the rectangular box outside of E, right? So this part I shaded in the red color. We should represent this part, okay? We should represent this part. So the event F will be event E union. What is this part in red? That is E's complement and F. Okay, E's complement and F. I think this part it takes time to understand. Okay, it takes time to understand this part. Let me draw it again. Okay, let me draw it again. So this is event F, and then event E in a small circle, which is inside F, Now, let's check what is E's complement. What is E's complement? E's complement will be, let me use black. E's complement will be all the part outside of the circle, right? All the part outside of the blue circle will be all those, right? Will be all those outside of the circle blue. Any internet problem? It's still going? Yes, yes. We'll continue here. Yeah, I think all the students are following. So, what is E's complement? E's complement is in the black color, right? E's complement is all the part inside the rectangular box, but outside of the blue circle, right? Outside of the blue circle. Now, how can we represent this red part? How can we represent this part? The one in the red circle, So I can take the intersection of the black part. I can take the intersection of the black part and the part with F, right? The part with F. So this color, okay, this color will be, I included F. I take F, and also it will included the outcomes in F as well in the E's complement, right? This one in the brown color, okay? In the brown color, I already shaded my F, but you understand the F is a red circle, right? So this part will be E's complement and event F. It occurs both in E's complement, which is outside of the blue circle, and then included in the big red circle in the event F. Okay, so that is the difficult part to understand. We rewrite the event F in this way. Okay, we rewrite the event F in this way. So so my event F, what is this one? So this event E is blue color, right? Blue one. What is this part? Brown, right? Brown. Make sense? So those two parts, of course, are formed the event F, right? Those two parts, one circle, blue circle, and inside, and this shaded brown part, that consists of all the event F. Then do they have any intersection? We don't need to define the event F. It's any event, okay? Any event F, just a subset. F is a subset of the sample space. Any event F, okay? Any event which is a subset of the sample space. And this proposition is true, okay? So here, what is the intersection of those two events? What is the intersection of those two events? Be careful. Here, I'm just talking about the relation between the event, okay? Between the event. So they are, the union of those two events will be the event F. What is the intersection of those two? Any intersection, any outcomes occurs in both, occurs in both blue and brown colors. Any outcomes occur in this way? So of course the intersection will be the null event, okay? Will be the null event. So here we can follow the axiom 3. Follow the axiom 3, we can do, you let your event, first event is E, your second event is E's complement F, right? So E1 in intersection of those two events, which is this one, that is the null event, and that is called mutually exclusive to each other. Mutually exclusive. So everyone is following me in the Rain classroom? Can you check the notes? Can you see the note in the slides? Then the probability of the union of those two events, which is the probability of event F. Probability of event F, that is the same as the probability of E union E's complement F, right? This is my event 2. And then that will be the sum of I from 1 to 2, PEI, which will be PE1 plus PE2, that is probability of event E plus probability E's complement of F. And actually the E's complement F, this is also an event, okay? This also defines an event, another event. So this is a probability, okay? It should be between 0 and 1. It should be 0 and 1. So this is the number between 0 and 1 plus probability E equals probability of event F. Of course, the right side, the left side, the probability of event F should be greater than or equal to probability of event E. That proves the proposition 4.2. That proves the proposition 4.2. Any questions? Anyone? Do you have any questions? Can you follow me? Can you follow me with the slides and my note in the Rain classroom? Because today we get a lot of internet and buffering problem. Alright, so that is the proposition 4.2, and it's very important. It's very important to understand in this theory. In this theory, let me use blue color to take the note. You can rewrite your event F in this way, okay? Those are two events, okay? This is also an event, and especially the intersection of those two events are null event. With the null event of two events, the mutually exclusive relation between two events, we can follow the axiom 3, okay? We can follow the axiom 3. Axiom 3 is the probability of union event from 1 to infinity, that equals the sum of each probability, right? Each probability. And trying to understand this is also event, right? This is also event. And the proposition, they gives the general case, okay? They gives the general case for all the event. If any event F is the sample space, okay? If any event is the sample space. Now, let's working on the 4.3, okay? 4.3. Here we have two events, okay? Two events, and we don't know the relation between those two events. E union F, okay? E union F, that equals the probability of event A plus the probability of F minus the probability of the intersection, okay? The AND event. This is also a new event, E and F. This is also an event. So I'm going to draw a Venn diagram to understand this one. I think I have the box already. Already have the box. Yes, I already have the box here. So here we only know that the E and F, they are just any subset of the sample space. And you might tell me there is no intersection for circle E and F. Yes, it's true. Okay, we can look at that later. That is special case. Okay, we look at more complicated case when they have some overlap. So that is the event E and F. Okay, event E and F inside the rectangular box, which means event E and event F, they are subset of the sample space. Okay. Of course, all those events we are talking about is the sample space. For example, we are talking about the experiment. When you roll in the die, what is the outcomes in the sample space? So that will be the number you got: 1, 2, 3, 4, 5, 6. Any event you are talking about, that will be the subset of all those outcomes: 1, 2, 3, 4, 5, 6. We are not going to call some other event you get the number 0 or you get the number 7, because those are outside of the sample space. Those are null events, and the probability, of course, it's 0. Make sense? So when you are rolling a die, we know we have 6 sides, and the number should be marked as 1, 2, 3, 4, 5, 6, and you are not going to get number 0. You are not going to get the number 7. Make sense? So this, when we are talking about the event E and F, we understand those are some events we are talking about inside the sample space. Like the event, you got the even number 2, 4, 6. You got the odd number 1, 3, 5. Or you get a number greater than 4, which is 5 and 6. You get a event. The outcomes is less than 3. So the outcome in the event will be 1 and 2. Make sense? So there is no need to define the event E and F. Okay, they can represent any subset in the sample space. Now, for those two events, we can separate. We can mark the region. Okay, we are going to mark the region 1, 2, 3. We are going to mark the region in this way. Okay, 1, 2, 3. And specifically, let me shade it with different color. Okay, let me shade it with different color. So part one here with the number part 1, that is in red color. Okay, that is in red color. And then I'm going to shade it the part 2. Let me try the yellow one. Okay, usually I don't use this yellow color, so part 2 will be this little part which is in yellow, right? Which is in yellow. And then part 3, let me choose blue. Okay, let me choose blue. Then that is part 3. Okay, that is part 3. That is part 3. So we shaded with different color for part 1, 2, 3. Okay, part 1, 2, 3. Now we can rewrite the event E union F in different ways actually. So we can rewrite E union F, and we know actually event E union F will be this part 1, 2, 3 together, right? It will be the part 1, 2, 3 together. So I can write event E union E's complement and intersect F. I can write in this way. What is event E? Event E will be the part 1 plus 2, right? 1 plus 2. What will be event E's complement? Will be all the part in the box outside of the circle E, and then intersect with F will be this blue part. So actually this, let me just explain with the color. So the event E will be the color red plus yellow, right? The part, the shaded region. And then what is E's complement? E's complement will be all the part outside of this circle E, and then intersect with F, right? Intersect with F, which will be the blue. So it's equivalent, right? It's equivalent, the right side and the left side and the right side. Or you can write it equals event F union F's complement intersect E. It doesn't matter, right? Because here F represents the yellow plus green. F represents the yellow plus green, and F's complement intersect E will be red, right? So F here will be blue plus yellow. And what is the complement F intersect E? That will be the red color. That will be the red color. They all represented E union F. There is no problem, right? There is no problem to understand, to rewrite the E union F in this way, right? Now, why we rewrite in this way? Because if you write E union F, they have the overlap. They are not mutually exclusive to each other. Of course, they have the intersection. The intersection is not the null event, right? But if we write either this way or this way, then let's check. Let event E1 is E, event E2 is E's complement and F, and I already marked the color here. Then E1 is red plus yellow, right? E1 is red plus yellow. E2 is blue. Are they mutually exclusive? This circle and this blue part, of course, right? Of course, E1 and E2 are null event. E1 and E2 are null event. So E1 and E2, we write in E1 and E2 just trying to make it in a standard way to apply the Angstrom 3. E1 and E2 are mutually exclusive. Mutually exclusive, right? Mutually exclusive. Now, let's write it. The probability of E1 union E2, that equals the probability of E union F. They are the same, right? This is P probability, as we said, it's a set function. It's about E union F, that is the same as E1 union E2, because E1 and E2 is this one, right? This is, we call the E1, this is E2. So they are mutually exclusive, so it will be P E1, which is P PE and PE's complement F, right? And then let's look at those two parts. Let's look at this one specifically. Okay, let's look at this one specifically. So is complement and F. Okay, is complement and F. So we can rewrite this part. Okay, we can rewrite this part in this way. Okay, we are going to separate the event F in this way. Event F, okay, event F will be the intersection of event E and F, and then unions in is complement union F. How can this one is true? Okay, is everyone follow me here? Let me finish this part. Okay, let me finish this part. So about this part, let me just write a new slide. So here we are going to work out this part. Is complement and F, right? Is complement and F. Now we are going to rewrite the event F. We are going to rewrite the event F as E intersect F union is complement intersect F. How can this one be true? How can this one be true? Distributive law, okay? Distributive law. F is like the common set, so that will be F intersect the union, E union is complement, right? E use, and this one means the intersect, okay? Intersect. And what is E? What is E? Union is complement. E is any subset of the sample space, and we already did that. Sample space intersects the event F. Of course, it's F, right? Sample space is the whole box. F is the subset. So this is true, right? According to the distributive law, this is true. And by the way, those two parts, okay, those two parts actually the E and F, the color, okay, E and F, these outcomes we shaded, it's in yellow, okay, it's in yellow, and E's complement intersect F, which is in blue, So those two parts from the Venn diagram, we know that the yellow part and the blue part, which is part 2 and part 3, they are mutually exclusive to each other. It's direct from the Venn diagram, part 2 and part 3. It's not working very well. Let me just finish the proof of this proposition, okay? So the Venn diagram, two events, E and F, and we separate part 1, part 2, part 3. This is event E, this is event F. So we shaded the part 2 is in yellow color, part 3 is the blue, right? Of course, they are SF means S intersect F. Why is F's complement? Take intersection, that means the outcomes occurs in the sample space, both in sample space and both in F. Why is F's complement should be event F? Okay, the question. So here, the part 2 and part 3, of course, they are mutually exclusive. Event EF, you can name this one as E1 again or as F1 again. And those two are mutually exclusive. Exclusive. So probability, it's union of those two, right? It's union of those two. So the probability of event F will be the probability of EF union E's complement F. And we know those two events, you can name this one as E1, another E1, E2, and they are mutually exclusive. So that will be PE1 plus PE2, right? Plus PE2. Now what is the probability? We are interested. Continue from the previous slide. We are interested in this one. So the probability of E's complement F will be the probability of F minus the probability E and F. Okay, don't be confused. Sometimes it's intersection, sometimes it's union. Now, what is the original? What is the original one? What is the original one? So that will be the probability E union F, right? Probability E union F. And then we separate, since those two events has overlap, then we separate as E union E's complement and F, and we let this is E1, this is part is E2. Why we rewrite E union F in this way? Because those two are mutually exclusive. The E is part 1 and 2. The E's complement F is part 3. So my event E1 is part 1 and part 2. And my event 2 is part 3. Of course, they are mutually exclusive, following the axioms, right? Following the axioms 3, so that is probability of E plus the probability of E's complement F. So that's why we continued here, why we need to find the probability of E's complement. What is E's complement? Will be probability of F minus probability of E and F. So will be probability of E plus probability of F minus the probability of E and F. So we prove that, okay? We prove that proposition 4.3. Probability of any subset event, any subset of sample space, event E and F. Probability of event E union F, that will be probability of event E plus probability of F minus the probability of the intersection. Now some of you might ask me the question, okay? Some of you might ask me the question. You give us the Venn diagram. It seems like there's some overlap. There's some overlap between E and F. Then how about they are mutually exclusive, basically? How about we have even E and F are like this? So what we proved in proposition 4.3 is this identity. Probability E union F will be probability E plus probability F minus the intersection of those two. So we analyze with the Venn diagram, but you give the overlap of those two. How about this case? So this case actually means two separate circles in a rectangular box, which means E and F are mutually exclusive. It's easy, right? There is no intersection. Mutually exclusive, what is the intersection of those two events? Null event, right? Sorry, exclusive. Mutually exclusive. So E and F is null event. Null event, what is the probability for null event? We mentioned that in the axiom 2. 0. So in this way, that's just the special case when E and F are mutually exclusive because the intersection probability is 0. So that will be the probability of each which is pretty easy, okay? Which is pretty easy, and it's just the special case. Special case. Make sense? So that is proposition 4.3, okay? I think you need spend some time. You need to spend some time to review the analysis of the 4.3, okay? We basically, when we apply, when we prove those propositions, we need to understand the event E and E's complement are mutually exclusive, and the union of event E and E's complement, they are sample space. They give the sample space, and it's important to apply the axiom 3 when we have two events are mutually exclusive, right? In those, we just repeat this axiom 3 again and again to prove those propositions. Actually, we have one more proposition which is more complicated, and we will do one more examples for this section next time. We can stop here today.